Good afternoon, good morning, good evening, depending on where you are. I'm Ernesto Galvão. I'm a research group leader here at the International Iberian Nanotechnology Laboratory, INL, in Braga, Portugal. I'd like to welcome everybody attending online to this 8th Quantum Portugal Initiative lecture. These lectures are a series of live webinars that we organize here to track the rapid progress of research and development in quantum science and technology in general. It's my pleasure today to introduce the speaker for this talk, Professor Carl Caves. Carl is one of the theoretical pioneers of the area of quantum metrology, which is the science of how to make the most sensitive measurements take advantage of quantum effects. Caves has degrees from Caltech and Rice University in the United States, and he has held teaching and research positions at Caltech, University of Southern California, and University of New Mexico. He was the director of the University of New Mexico Center for Quantum Information Control since its foundings in 2009 until 2018. He's now a distinguished professor, emeritus, and research professor at physics and astronomy at the University of New Mexico. So he's joining us from a time zone much earlier, and he's having his coffee, I can see. Carl is a fellow of the American Physical Society, American Association for the Advancement of Science, and a member of the US National Academy of Sciences as well. Our paths have crossed in the past in both Canada and Brazil, and it's a pleasure to host him now in Portugal, even if it's a virtual meeting, for a talk describing his various research interests over the years. I can see we have many attendees already joining. So for the people watching this talk, if you have questions, please post them on the chat channel on Zoom. And at the end, I'll pick a few to ask to our invited speaker. So without further ado, let me invite Professor Carl Caves to give his talk. Carl, thanks again for accepting our invitation to give this lecture. The stage is yours.
What happened there?
I think I heard you, so.
Yeah, well, I just need to go back there and share the screen on the Zoom content, which I failed to do. My wife's mouse which I'm using her computer, is a little more finicky than mine. So there, did I succeed in sharing the screen? Yes. So now I just need.
It's not in presentation mode yet, but yeah, we can see it.
We're going to get into presentation mode. I think we are. I think it's already done that. There we go. All right.
Actually, sorry. It is. Sorry, it's working now. Yeah, cool.
All right. I'm going to be talking to you about a long history of what I think of as quantum metrology, even before it was called quantum metrology, to where it is now, where we think of it as a piece of quantum information science. And to get started on that, I would like to first draw your attention to the fact that I have these slides with green borders, which are meant to show you the parts of the world that I find inspirational. And also, I might stop and see if there's any questions when we get to these green slides. So keep that in mind. Submit your questions as we go along, and I'll stop and see if there's any that Ernesto thinks I ought to attend to when we get to one of these green slides. All right, quantum information science. It's a new way of thinking. It's a new way of thinking for computer science. And that's a triumph for us physicists in the sense that computational complexity depends on physical laws. So it's not some abstract thing that you can make up independent of the way the world works. It depends on the way the world works, and it depends on the fact that the world is quantum mechanical, ultimately. On the other hand, physicists have learned a few things from quantum information science as well. When I learned quantum mechanics was a nag. That is, the uncertainty principle restricts what can be done. Whereas the point of view of quantum information science is that quantum mechanics is a liberator. The question you ask is, what can be accomplished with quantum systems that can't be done in some cases at all in a classical world? And the reason is that quantum mechanics escapes the constraints of the classical world in the sense that we cannot describe what's happening in quantum mechanics using the language of realism that we apply, that we learn. We all learn, it's part of us that we learn to describe the classical world. Another way of saying what quantum information science is this sort of quantum engineering where we explore what quantum systems can do instead of being satisfied with what nature hands us, instead of what we originally did with quantum mechanics, which was to explain various phenomena out in the world. We ask, what if we take those same systems and ask what they can accomplish, instead of just letting them do what comes naturally? And the main example I'm going to be talking about now, which is incredibly self-serving because it's what I did, is an example of that, although that's not how it would have been thought of at the time it was proposed. So that's one theme of the talk, exploring what quantum systems can do instead of being satisfied with what nature hands us. The other theme is specifically from metrology. You could say metrology is the heart of physics because it's the way we extract information from physical systems. It is the way we extract information about the world around us. And we have, in metrology, we have this conflict between quantum mechanics as a nag and quantum mechanics as a liberator, because we still have to worry about what restrictions does quantum mechanics put on the measurements we make. We're still asking the question, what can we do if we don't let nature just run off and do what it wants? But we have to pay attention to the restrictions, in essence, imposed by the uncertainty principle. So a second theme of this talk is going to be about the way we do theoretical physics. And this is important. The way we do theoretical physics involves ultimately narratives about how the world works. If your math gets so complicated that you can't give a narrative, then you kind of run off the path because nobody can use what you're saying about the physical world. And so it's very important to have narratives. And in this case, it's going to be narratives about noise in physical systems. There is, however, another thing we could be doing in theoretical physics, and that's increasingly come to the fore in quantum metrology. That is, we can give proofs, analytic proofs about how well you could measure certain things. And this is important too. But it often misses the point of the narrative. That is, if you know the proof, you don't have a clue what to do. You just know you could do it. And you know you couldn't do any better. So that's going to be one of the second theme of this talk. And let's now get started on talk. We're not going to bother to take questions here because it's too soon. But let's get started on squeeze states in optical interferometry, which is going to be our main example of asking nature to do something other than what comes naturally. And of course, this is now one's able to put this in the context of actual implementation in real world devices. It's kind of silly to call them devices because they are these massive interferometers that are used to detect gravitational waves. So I pictured here the three current working gravitational wave interferometers. There's two in the United States that make up the Laser Interferometer Gravitational Observatory, LIGO, so I'll call it LIGO throughout. Those two interferometers are in Hanford, Washington, in the northwestern United States, and Livingston, Louisiana, and the swamps I hope they're not being constantly flooded out by hurricanes, but actually, I'm sure they are. Anyway, we have these two big detectors in the United States, and there is also a big detector in Europe called Virgo, named after the Virgo cluster of galaxies, and that's in Italy. That's a 3-kilometer arm interferometer. And how do these interferometers work to detect a gravitational wave? Well, you'll see up there at the upper right a picture taken from a LIGO publication. It's a very simple picture. The way we describe a gravitational wave is in terms of a quantity called h. That is the the perturbation of the metric away from flat space in linearized gravity. And it is also the strain introduced in these interferometers. So you see there a depiction of that strain oscillating sinusoidally. And then below it, you see the way the interferometer, the way that the interferometer responds to that. So at the first peak, the horizontal arm has been extended, the vertical arm has been shortened. Then half a cycle later, it's just the opposite. The vertical arm has been extended and the horizontal arm has been shortened. And so you would detect the gravitational wave by, so the end mirrors are actually free masses. They're hung from pendula, so they're effectively moving freely. And what you are detecting, or what you're attempting to detect, is the differential motion of these interferometers as a gravitational wave comes by. This depiction is for a gravity wave that's going straight into the screen, and it has the right polarization. There's two polarizations. Things will look a little different if the gravity wave is, for instance, coming from the right or coming from above or coming at some other angle. But essentially, this is the picture. The gravity wave oscillates the interferometer, and that's what you're trying to detect. Now, if things were as depicted here with the kinds of displacements. Oh, so I just mentioned, h is the strain, that is, it is the motion of the mirror divided by the length of the arm. Okay, so it's a dimensionless quantity. If things were as depicted here, well, heck, we could run outside and detect gravity waves ourselves, because actually we would be stretching and contracting by quite large amounts when a gravity wave comes by. The problem is h is not very big, even for the most violent events in the universe. So let's just look at that. This is the kind of zero order calculation done by relativity theorists, primarily Kip Thorne, to try to figure out how big does h get, and what kind of interferometer would you need to design to detect the gravity waves. So this is, most of you probably aren't astrophysicists, but this is the way astrophysicists do things. And I used to be an astrophysicist, before I knew what I was doing. So how big is the h from let's say the coalescence of two black holes, which have a total mass m? Well, you just think there's one dimensionless quantity that we can make up out of the mass, the distance, how far away those two coalescing black holes are. We're calling that capital R. The dimensionless quantity you can make up is the so-called dimensionless Newtonian potential, Gm over c squared R. And that will be the size of the gravity wave you would expect to get at a distance R from the source, if all the mass energy of the source was radiated into gravitational waves. Well, we'll put in a fudge factor because it's not true that all the energy goes into it, but we'll say this is a strong field source, two black holes coalescing. And so the amount that goes into gravity waves, we're going to say a tenth of the mass energy goes into the gravity waves. That appears as a square root here because h is basically a quantity that is an amplitude, and the square of it is energy. So When we have an energy quantity like this efficiency, we have to put a square root in to turn it into a strain. So now you work this out in the typical way. An astrophysicist would, you say a tenth of the energy goes into, of these two black holes, let's say, goes into gravity waves. We say they have a mass of 10 solar masses, and we say they're a gigaparsec away, which is a long way. That's essentially the edge of the universe. It's about 3 billion light years. And you find out it's the strain you need to detect is 10 to the minus 22. That is, those masses are going to move by 1 part in 10 to the 22 of 4 kilometers. Pretty small, you know, a tiny fraction of the radius of the nucleus of a single atom. And that's what you need to do. The other thing you really need to know is what's the time scale. And there you just do some more dimensional analysis. You say the time scale of anything that's governed gravitational is c cubed over gm. And then we put in a fudge factor there, delta, because typically things aren't quite as fast as the gravitational time scale. And you find out that a typical time scale for the sources we've just mentioned is about 200 hertz. So you need to be detecting the motion of these end mirrors at the level of 10 to the minus 22 in strain sensitivity and at a frequency of 200 hertz. So it's a burst event, but the peak frequency is at 200 hertz. This is basically the duration of the event and the peak frequency, okay? All right, we need to do that, and of course they did it. Here's the famous publication from 2016 where you see the signal from the Hanford detector and the Livingston detector. That's the strain signal seen by the two. On the right, the Hanford signal has been turned over and inverted because of the time delay and the particular way the interferometers are oriented. And you can see they did a pretty good job of getting the same signal. In fact, anybody who looks at this is going to say, this is sort of unmistakably two massive objects running into each other. There's a depiction of that below and of the kind of waveform that would be predicted when two black holes come in. You first see them spiraling in gravity waves at twice the frequency of the orbit. And then the two coalesce. There's a big burst. That's that big thing toward the end. And then the black hole shakes a little bit at the end, and that's the very end of the signal. Increasingly, they can see all of these different things and start to actually think about testing relativity. But for this event, the two objects were quite big, bigger than most astronomers expected. The two objects were roughly 30 solar masses apiece for a total mass of 60. They were about 410 megaparsecs away, that is 1 billion light years. And the energy radiated into gravity waves was about 3 solar masses, so about about 5% efficiency compared to it. So that's a heck of a lot. While they were on, which was for 100 milliseconds, they outshone in gravity waves the entire luminosity of the visible universe by about a factor of 100. So this is an enormously powerful event. But by the time it gets to us, well, it's very hard to notice it. And that's why they had to build these billion-dollar machines to detect it. All right, I'm going to pretty much skip over the rest of that introduction to gravity waves. That's the kind of thing they had to detect. And how did they do it? Well, they had an initial LIGO, which had a strain sensitivity that was pretty good, but not good enough to detect anything. And then they closed it down for several years, preceding 2016. And they turned it back on with a differential strain sensitivity of about 10 to the minus 22, a displacement sensitivity thus of 4 times 10 to the minus. We can't even see what I'm so used to doing things by just punching on the phone, and this machine won't let me do it to move everybody's picture out of the way. 4 times 10 to the minus 19 meters. I could do that math, but not while I'm giving a talk. That's from this, that strain sensitivity applies from roughly 50 hertz hertz to about 2000 hertz. So this is a remarkable accomplishment. It cost $1 billion. They turned it on and immediately detected that event that I said. And at the time, they were detecting events at roughly 1 every 6 weeks to 2 months of this character. All right. Now, how did they do that? Well, what's actually in this interferometer is a so-called, there's a powerful laser in this central building. You can see at the bottom of the Livingston photo. Then in the arms of the interferometer are Fabry-Perot cavities that store the light for roughly a millisecond. So that allows the gravity wave signal to build up on the time scale of a typical gravity wave. They used what's called power and signal recycling. That's not letting any light be wasted and also tailoring the frequency response of the detector to the kinds of signals they detect. And finally, in the third observing run, they put in squeezed light, and that's what we're now going to talk about. All right, so now we're not going to think about that very complicated interferometer, at least for a while. There is an easy way to think about it, but we're going to think about it in the way that I thought about it in 1981, when I proposed putting squeezed light into gravity wave interferometers to make them work better. So here's a schematic of a Mach-Zehnder interferometer. You see the laser that is powering the interferometer. We're going to, and then, so you see there's 2 ports coming into the interferometer. There's the laser port, and then the port typically that has vacuum. The light divides the interferometer. We're just going to draw the phase shifters as pieces of glass that give a phase shift here called phi/2 and minus phi/2. The interferometer detects differential phase shifts. And then you recombine the light at the final beam splitter. You detect, let's say, if you're doing difference detection, you will have photodetectors that detect the photons coming out in each port and subtract the results, and you get an interference pattern shown up there on the upper right. And that interference pattern is a function of phi. So this is the differenced signal as a function of the phase shift. We're regarding the operating point as being that little dot there where the equal amounts of light coming out in the 2 arms, and the effect of a gravity wave or of the phase shift is to move you slightly up and down on that curve, and that's what you want to detect. So the curve is phi changes, you move slightly up and down on that curve, and then you detect a signal. Now, the gravity wave interferometers in LIGO work nothing like this. They have big cavities in the arm, and they work on the null fringe on the output, where essentially no photons come out in the bottom port of their detector. That's a detail. It's actually a little hard to understand, but you know, that's why I'm not talking about it. It's a little bit hard to understand. But, so let's look at this. All right. So we're going to depict the light in this interferometer as little arrows. So you can see what appeared there is the laser light is depicted by an arrow that depicts its amplitude and phase of oscillation. And that's meant to mean that it has the length of the arrow is the amplitude and the phase is the direction of the arrow. And this is meant to mean that the light is, if you sit at a point, it is oscillating as cos omega t. If we had a vertical arrow, it would be oscillating as sine omega t, okay? Now, we have to think about the light coming in the other port, and we're just going to imagine there actually is some light coming in the other port. That could be from a thermal source, so it's fluctuating light. It could be you're actually putting something in there. We just need to understand what happens to the light that comes in what's called the vacuum port. Ultimately, there's nothing there. Ultimately, there's nothing there. But that light has 2 phases. The blue arrow is the light that's in phase with the laser, and the green light, the green arrow, is the piece of that light that's out of phase with the laser. All right, so what happens after the beam splitter? Well, in each arm, you get interference between the light coming from the laser and this imaginary light coming in from the unused port. And you can see there what happens. The light that is in phase with the laser adds to the amplitude in one arm and subtracts from the amplitude in the other arm. And this is required by unitarity, or more prosaically by energy conservation. Because if you increase the energy, the amplitude of the light in one arm, you must decrease the amplitude of the light in the other arm, or else energy won't be conserved. So this is guaranteed by energy conservation, and hence by unitarity. So what happens to the light that's out of phase with the laser that comes from the vacuum side? Well, that light, let's say, changes the phase in the upward direction in the horizontal arm, but it must change it in the opposite way in the other arm by the same unitarity argument. So once you give me that argument, you're finished. This is the argument. The light that is out of phase with the laser coming from the vacuum port changes the phases differentially in the two arms. That is, if there's an advance of phase in one arm, there is a retreat of the phase in the other arm. That's exactly what the signal does, and exactly what the interferometer detects. So what one can see without any further analysis, you don't have to write any equations. This is a story. This is why this is important. It is a story that tells people what to do when they design an interferometer. What you can see is that it is the noise in the out of phase light in the vacuum port that is responsible for the noise in an interferometer. And if you want to do better, you need to change that noise coming into the vacuum port. You need to reduce the noise that's out of phase with the laser. That's the whole story. Now, so there's a bunch of junk here that I could talk about, but I'm not about to do it. I'll say everything. The point is, you need to reduce the noise that is out of phase with the laser to make the interferometer have a better shot noise sensitivity. All right. And how can you do that? If it's vacuum coming in that port, it is the vacuum noise that's responsible for the noise in the interferometer. That's the first thing. The noise on the laser is irrelevant. That's common mode noise, and the interferometer is insensitive to it if the interferometer works right. The noise in the interferometer is due to the vacuum port, and that's what you need to change. That's where you need to stop letting nature do what it wants and do something different. You need to squeeze the light in that arm, because reducing the phase noise will inevitably increase the amplitude noise by the uncertainty principle. All right, you do that, things are better. I am going to make one little caveat here. I'm not here talking about the back action noise. There is additional noise in a gravity wave interferometer, because the light, the radiation pressure of the light pushes on the mirrors. And it is the amplitude noise coming from the vacuum port that does the differential pushing on the mirrors. That's important. It's not currently important, even now, in a gravity wave interferometer, but it's important to understand. But I'm not going to be talking about that, because it just makes things too complicated. So we're only talking about what's called the photon counting noise, or the shot noise. All right. So here's a depiction of squeezed light using the same kinds of phase diagrams. The two components that I've been talking about are typically called X1 and X2. They're called quadrature components of the light. And coherent light is represented by a little circle. So where it's sitting represents the amplitude of oscillation of the light. And the little phase, the little fuzzy ball around it, the ball on a stick, represents the noise. And over on the left is a depiction of how the noise is in the electric field, which is actually oscillating. Squeeze light that reduces the amplitude noise is shown on the second of those two charts. So that has reduced amplitude noise and increased phase noise. And you can just see when you look at the electric field, the zero crossings are poorly defined. That's the fact that the phase noise is big, but the amplitude noise is small. And the opposite is reduce the phase noise. And that's shown on the left. You can easily see the zero crossings are well defined. That's the phase noise is reduced, but the amplitude of the wave is increased. Now, one of the reasons I like to give this talk is this is the drawing I drew in 1981. And it was published. And it's still an important to understand because it is the story of squeezed light. I will mention that the light they use in LIGO is vacuum squeezed light, which is going to be depicted over here on the right. So development of squeezing took a long time. The early work that ultimately led to what they use in LIGO was done by Jeff Kemble, first at Texas and then at Caltech. And I'm depicting here an experiment done by some German researchers reported in 1997. And I like it because they basically tried to reproduce my pictures. And I'll just, so they had these light, they did tomography on these light beams and basically showed this is the kind of noise you get. And the bottom light is the phase squeezed light. And you can see what it does. It just has fluctuations that it has noise that oscillates in time. And that's the kind of light you use in LIGO. All right, they had squeezing by a factor of about 3.5. These days you can get factors of tens or hundreds, although most of that is not useful in LIGO because of inefficiencies in LIGO. All right, so a bunch of people pushed this forward further. The main thing that had to be pushed forward ultimately was to get the squeezing from megahertz sideband frequencies about the carrier down to audio frequencies, so it's useful in LIGO. All right, so here's where the Hanover group was in 2010. They had squeezing, so you can see a picture of the apparatus, you can see their noise, you can see the flat line there is the shot noise, and then you can see that they had about 8 to 9 dB below shot noise at audio frequencies. They are now able to do 20 dB. All right. Ultimately, this was put into a real gravity wave detector, although not one that detects anything because it's not quite good enough, and that's the geo detector. Oh no, sorry, I removed that slide. So ultimately, this was put into LIGO. In observing run 3, it was put into, no. This is an early experiment, a test, just before LIGO shut down in 2013 to make advanced LIGO. They put in squeezing. You can see the noise spectrum over here on the right, and you can see they achieved about 2 dB of shot noise reduction by using squeeze light. They had considerably more squeezing than that, but they only got about 2 dB of noise reduction because of inefficiencies in injecting the light and losses in the actual system. All right. Now we come to quantum metrology actually making a difference. That is, LIGO and Virgo both put in a squeezing in 03. They turned on those detectors. The event rate went up by about a factor of 10. A good part of that was due to squeezing. And you can see here I put here so there's reports from both LIGO and Virgo. I put in here the LIGO Livingston data. The black line is shot noise. The black line is without squeezing, and the green line is the reduction in noise from having put in squeezing. So here, if you live long enough, if you had a good idea and you live long enough, you get to see somebody actually do it. Of course, somebody had to spend $1 billion, and dozens of experimenters had to work hard over 40 years to make this happen, but it did. And it is essentially the only example of quantum metrology making a difference. There's now another example in dark matter searches where, again, they're using in this case, squeezed microwaves to improve dark matter searches for axions. All right. I just want to give you another way of thinking about why squeezed light works. So here I've depicted something that's a bit more like what they actually have in LIGO and Virgo. The laser produces light that goes out through a beam splitter and then enters these two cavities. They're big Fabry-Perot cavities, 4 kilometers long. The beam size is roughly this big on the mirrors. And I hope you can see me, it's roughly that big. These are big cavities. The amount of power is enormous. I'll get to that in a minute. But a way to think about what happens is the light from the laser excites the symmetric mode of oscillation of the two cavities. And that symmetric mode of oscillation, if nothing happens, that light just exits the interferometer back toward the laser. And I put in the power recycling mirror. The point of power recycling is don't waste that light, put it back in. And that's crucial. That is absolutely crucial to the working of the LIGO interferometers. Now, if we did put light in from the vacuum port, or what they would now call the antisymmetric port, we would excite the antisymmetric mode of oscillation of the two cavities. So the symmetric mode, the two cavities are just oscillating along in phase. And let's see if I can walk and chew gum at the same time. They're oscillating out of phase when you excite the antisymmetric mode. What a gravity wave does is push the mirrors differentially. That causes a transition from the symmetric mode to the antisymmetric mode, and that light then exits the interferometer in the down direction into the antisymmetric port. So you can see immediately that it is the noise from the antisymmetric port. That is the whole point. Any noise that comes in from the laser excites the symmetric mode and just disappears. And if you're detecting down here in the vacuum port, well, you don't have to care about that. It is the noise from the antisymmetric port that counts, and that's why you need to squeeze it. There could be some immediate questions there, but anyway, let's go on and look at this. What are the actual numbers in LIGO? The laser produces about 20 to 30 watts of power. Beyond the recycling mirror, they produce about 700 watts to a kilowatt. Heck of a big deal. That's why the recycling mirror is important. And then inside the cavities, there's currently about 100 to 150 kilowatts circulating power, maybe 200. Design was supposed to be a megawatt, and they weren't able to do that. And that's why they had to put in squeezing. Because you can see from this, what are the numbers? This number amounts to 4 times 10 to the 18 photons per millisecond entering the interferometer at the beam splitter. That's a heck of a lot. And the reason they can do that, photons are cheap. And as long as they're cheap and you can get more of them cheaply and have them work, well, then you're just going to do that. You're not going to bother with any squeezing. You will just do that. The more photons you have, the better off you are. But what happened was that about 150 kilowatts circulating, everything got semi-unstable, and they really find it very difficult both to jack up the laser power and to control the interferometer with more power than that. So now they're stuck. They have to do something different. And the point is, if they wanted to get a factor of 10 a factor of 3 improvement in sensitivity, they would have to jack up the power by a factor of 10. That is, they'd have to put in 10 to the 19 photons per millisecond. But they can get the same effect with 10 dB of squeezing, which amounts to 2.5 squeezed photons per millisecond. Now, those are magic photons. Those 2.5 photons can do as much good as putting in another 10 to the 19 photons from the laser. And that's why squeezing is important. Of course, this way of explaining it is totally misleading. because it's not the power in that counts, it's the interference of the squeezed light with the light with the laser light that counts. And that's why this tiny amount, apparently tiny amount of squeezing can be as important as jacking up the laser power by an enormous amount. All right, I just want to give you a little bit of history. The ideas that made LIGO go optically are all due to Ron Drever. He proposed putting Fabry-Perots in the arms. He figured out how to make that work by using what's now called Pound-Drever-Hall locking to get the light into the cavities. And he proposed the techniques of nested cavities, that is recycling, that are absolutely essential to make the thing work. Ron's a hero of mine. And then I had one idea, squeeze light, and it turns out to be important too. But I don't want to draw attention to the fact that my idea was important without drawing attention to the fact that all that is built on classical techniques that were invented by Ron. All right, so when Ron's eyes asked after 35 years, you had to put squeeze light in. And there's a little quote from my paper in 1981. Experimenters might then, that is now, be forced to learn how to very gently squeeze the vacuum before it can contaminate the light in their interferometers. I see that at the time I still wrote with split infinitives, but anyway, perhaps that's forgivable. All right. All right, let's just see if anybody has any questions. Any important questions at this point?
I think we can probably go on. People are kind of shy.
All right, and yeah. For the organizers who are worried that I'm not going to finish on time, everything's set. All right, so that was about thinking about an interferometer and the noise sources in it and how the noise runs around. That is, it's telling stories. Moreover, it is an example of not accepting what nature gives us, which is vacuum coming into the unused port, but stepping in and saying, geez, let's do something different. It is the kind of zero order, simplest way to do something important in metrology. Squeezing, that's why it's used. It's simple to understand, and it's kind of simple to implement. Now I want to get on to the other way of thinking, the kind of thing that quantum metrologists do now, which is looking at systems and seeing how can we say, well, you have a great story there, but how do we know there isn't another story that would work better? How do you know that? Well, how do you know that some other technique than putting squeeze light in, totally different, would make the whole interferometer work better? So that's what I talk to you about now. And this is important. And this is what quantum metrologists tend to do now. So I want to introduce that just by noting that the optical interferometer, here is what we ended up with its sensitivity. 1 over the square root of the number of photons with an uncertainty in that phase quadrature, reducing the noise. The so-called quantum noise limit or shot noise limit is when the 2 quadratures in the unused port have the same amount of noise in them. And that gives you the shot noise limit, which is 1 over the square root of n. There is a thing called the Heisenberg limit, which is important. And that you can get from this by saying, well, what if we put so much squeezing in that the amount of power in the squeeze light approaches the amount of power in the laser light. So this quantity uncertainty in X2 itself goes as 1 over the square root of n. Then you will get a sensitivity that goes as 1 over the number of photons, and that's called the Heisenberg limit. And that's the thing we're going to be talking about. And what we want to ask is, when do these limits hold? And do we think they're limits only because we haven't thought hard enough? that is, have our stories misled us? Are there better things you could do? All right, I'm gonna skip over that. And to answer that question, one of the tools, the main tool that's used, is a thing called Fisher information. And I just want to run you through where the Fisher information comes from. The Fisher information, it's a very mysterious quantity because it shouldn't have been called information, because everybody starts thinking about things that have nothing to do with it. But here's where it comes from. We can motivate the Fisher information just by talking about polling, where we walk up to somebody and say, do you favor this candidate or this candidate? Okay. And we might want to estimate the probability that people favor one candidate or the other by polling a lot of people. We're going to poll capital N people, and then little n of them will favor the first candidate, and we'll call that the frequency of occurrence of the first candidate. That's n over big N. The mean value of that is the probability, and the variance of that simply goes as PQ over N, where Q is 1 minus the probability. Now you can do something with this. We can measure the distance between neighboring probability distributions in units of their distinguishability. So we imagine there's two different probability distributions, and we're trying to tell if the actual population has this probability or a nearby probability, actually very nearby, that is delta P away. And we will measure how well we can determine delta P in terms of the variance and the frequency. So you just work through that. And it turns out to be this quantity written here on the right, that is delta P squared over P plus delta Q squared over Q. That's the Fisher information. And this is where it comes from. And it answers an important question. Why didn't we use absolute delta P plus absolute delta Q, or delta P squared plus delta Q squared, or delta P over P squared plus delta Q over Q squared? All of those are potential measures of the difference between two probability distributions. But the one that comes from sampling is the Fisher information, delta P squared over P. You can get a nice feeling for that in terms of taking a square root. And here you get very tempted to think there's something quantum mechanical there, because this distance between distributions, when written in terms of the square root, is the Euclidean distance. And the apparent line becomes a piece of a sphere, and that's true generally. That's what the Fisher information does. I'm not going to dwell on that. So there's a thing called the classical Kramer-Rao bound. For any parameter that affects a probability distribution, if you measure that distribution, that is, measure the quantity J, and you process that information in any way you want to estimate the parameter, it's a simple proof, it's a few liner, that the uncertainty in your estimate is bigger than or equal to 1 over the square root of n, the number of times you sampled, and 1 over the square root of f, which is the Fisher information. And the Fisher information is just that thing I just wrote down. So this is a really easy thing to get. It is absolutely fundamental, and it is the tool we use to address questions in quantum metrology. All right, now we need to get to interferometry. And here comes another step that, this is important in theoretical physics. I've drawn interferometers that look kind of like what is actually out there in the world. And now I'm going to draw one that looks nothing like what's out there in the world. And this kind of abstraction is exactly what theoretical physicists have to do. So what we imagine is there are photons with two modes. The two modes are the two directions in the interferometer. We're going to call those 0 and 1. Or perhaps there's atoms with two levels, 0 and 1. And we're going to treat all of those atoms or photons independently. And they go into this circuit diagram. The first stage of it is the beam splitter, which in this picture is called the Hadamard transform. And that simply changes each of the photons to be in a superposition of 0 plus 1. So that's a superposition of going in this arm and going in the horizontal arm and going in the vertical arm. Then we impose the phase shift. There's a mathematical way to do that, but that puts phases on the two pieces. you can't measure those phases directly. So the point of the last beam splitter is to change that phase information into amplitude information. The last piece is just do the beam splitter again. And now we have our sinusoidal interference pattern, where depending on phi, the output is either in this arm coming out, sorry, the horizontal arm coming out, or the vertical arm coming out. So this picture is exactly equivalent to an interferometer where the photons are independent, and that's what we want to change. But you have to think a lot to see, how does that picture from the world map onto this? We need to do it, so we just did it. Where does the Heisenberg limit come from? Well, we dropped this idea that the photons act independently, and we use what's called the controlled knot gate. So the top photon here goes through the beam splitter, and then we do what's called controlled knot, which changes the state of the other two photons depending on the state of the first photon. And we end up with a superposition nothing like what we had at the top. We have a superposition of all the photons going in the horizontal arm and all the photons going in the vertical arm. Then we put the phases on. We undo everything, and we get the same kind of fringe pattern, that is interference pattern, that we had before, but it's n times as big. Well, geez, that's terrific. When you can make your signal n times as big, you're certainly going to do better in detecting the signal. All right, so now this is called a Cascade Interferometer, and now we're just going to abstract more. This is what we do as theoretical physicists. We just abstract away until we don't even understand what we're doing. But you cannot lose the connection to the world. But anyway, that's what we do. So now we say there's a bunch of things that regarding them as photons. There's a bunch of things that enter this circuit. They're in a standard state S to start with. They undergo an arbitrary joint unitary operation. Then we impose a signal. So the first thing is state preparation. We have them in a standard state, and then we put them through a unitary. Then we do the dynamics, which is imposing the phase signals. And then we do the measurement. And the measurement here is made completely general. Now we're cooking, because we can use a very general formalism of Fisher information to figure out what's going on. And that was done by a whole set of people in different ways. So I just repeated that interferometer picture, and here's what we can prove. The dynamics here is assumed to be separate from the different systems. That's an important assumption. We could drop it. I could give a whole talk about that, but I'm not going to give that talk. And here's what you can prove from the Fisher information, that no matter how you sample the outputs of these measuring devices to determine the phase shift phi, your estimator is greater than or equal to 1 over the uncertainty in this dynamical object at the point where the systems enter the dynamics. So that's a powerful thing. It's often called the generalized uncertainty principle, because you can see that the uncertainty in your estimate times the uncertainty in some quantum mechanical quantity is greater than or equal to 1/2. It's the right kind of uncertainty principle, because it actually has to do with measurements that you make and limits on those measurements, not limits on imaginary things, as in the standard uncertainty principle. All right. Now we can just work with this. It's pretty easy to see that if we if we take this Hamiltonian little h and say that lambda is the eigenvalue of its, and we diagonalize it, and we say lambda is its largest eigenvalue and little lambda is its smallest eigenvalue, then the uncertainty is bigger than or equal to, is less than or equal to 1/2 the number of systems times its difference in eigenvalues. That's a trivial thing to show. And that gives us the Heisenberg limit. That is, we know, no matter what you do, your parameter estimation is limited by something that goes as 1 over n. If you insist that this V up here, this unitary up here, acts separately on the different inputs, it's a trivial thing to show that the biggest uncertainty goes as the square root of n. And so the phase uncertainty goes as 1 over the square root of n. That's called the quantum noise limit or the shot noise limit. So there we have it. These things, you can just prove them. Now, of course, there are assumptions in those proofs. And the point of proofs in physics is to see where the assumptions are so you can go out and see if you can violate them. That's the point of a proof in physics. But these are pretty strong assumptions. They're hard to violate. And they say that these two limits, the shot noise limit and the Heisenberg limit, are absolutely fundamental given the circumstances you're in. So this is the kind of proof that you can give. And I'm just going to skip over this. You can see you can achieve the Heisenberg limit. What? I just want to talk about what we really do and what many quantum metrologists do is to realize that the Heisenberg limit is irrelevant in systems where you can buy a lot of photons. There's no way, given losses, that you are going to achieve the Heisenberg limit, certainly not in LIGO, because you're suggesting that you would have an amount of squeezing that had 10 to the 19 photons in it. That ain't gonna happen. It ain't gonna happen because you're not gonna get that amount of squeezing. And it's also not gonna happen because losses in the interferometer will mean all of that squeezing was useless anyway. So a huge amount of work goes into quantifying how well you can do it. Losses, I'm not going to discuss that much here. I just referenced a particular analysis that was done by one of my students in his dissertation in 2015. But this is a kind of general answer. In all kinds of situations, this is the kind of general answer you get for how well you can do in the presence of photon losses. All right. So where we end up? We had a little example of making the world do what we want instead of what comes naturally, which is to be in vacuum. And, you know, to make that useful in the LIGO interferometers, that took 40 years. So it's hard to make nature do something that, that it doesn't want to do and to make it useful. So quantum metrology is hard. Basically, that's the statement, is you will use classical resources as long as you can to make sensitivities better because classical resources are easier to get at. What I want to just focus on here at the end is this difference between telling stories or narratives about the way physical systems work and giving proofs. So the squeeze light narrative is about understanding fringe patterns and sources of noise and designing devices to improve phase sensitivity based on this understanding. This is telling a narrative about how physical systems work. The quantum Cramer-Rao is important. Those bounds are important because they prove what we can do, but they are in some sense misleading and they are clueless on practicality. Why are they misleading? Because what did the Cramer-Rao bound say to do? It said to make something very uncertain. It said to make that Hamiltonian that imposed the phase shifts very uncertain. Well, that's not a lesson that an experimenter wants to hear, that the way to make your experiment better is to put more noise in. But that's what it means. The way that is constructed, that is making the other quadrature, in the squeeze light example, making the other quadrature of the squeeze light uncertain. That is what it is. That's what the Cramer-Rao tells you. It just assumes that you're in a pure state, so that when you make that very uncertain, the quadrature you're interested in has very little uncertainty. But if you don't understand what you're doing, geez, you don't even know what this is about. You've just proved something. It's important. It verifies whether our stories are fooling us, but it very often misleads you about what you should do in an actual experiment. So, which is better, stories or proofs? Well, you need them both. You know, I learned how to do them both. And you need to do that too if you're going to work in quantum metrology. The point of this talk is it's not enough to learn how to do proofs. You must understand how your proofs apply to actual systems. And if there's a moral to what I'm telling you, that is the moral. All righty. Let's finish up. Squeeze light into the vacuum antisymmetric port is the optimal strategy for optical interferometry. That's what the proofs tell us, and they've done it. And I'll just quote a slogan to you: the scientific truth shall make you free. That's what it means to be a scientist. Learn the truth. Find the truth about how the world works. It will make you free. Thanks. So I'm ready to do some questions. There could be more to this. Oh, there is. Yeah, thanks for your attention.
Thanks a lot, Carl. Thanks a lot. Yes, so please feel free to ask questions in the chat. Everybody who's watching, attending. It was a wonderful talk, Carl. Very nice to see your take in the story, right from the beginning. I was wondering if I may ask a question while people, mobilize here in the chat. I was wondering about different applications of quantum metrology, because you said something like, at some point, you said the place where it made the difference was in LIGO and to some extent in dark matter experiments, right? But you have these sensing techniques with nanodiamonds and single artificial atoms, for example. I guess that's somewhere else where you may get an advantage, right, from using quantum systems for metrology. I think the setting's a bit different. Can you comment a bit on this kind of application using single?
Yeah, there's certainly other cases where there are certainly other cases where you can do things where there is an improvement due to using quantum techniques, such as the ones you're mentioning. There are various entangled, that is actually two-mode squeeze states, ways of doing things. For instance, what Eugene Polzik does, where you can find advantages due to quantum metrology. I am currently thinking, although I'm happy to be educated, that none of those does things that are intrinsically better than what you could do in another setting. That is, they haven't measured anything better than could be done using a different technique. And that's what's been done in LIGO. You could not do these measurements without, that is, you could not achieve this sensitivity presently without using the squeeze light techniques. Back in the 80s, people demonstrated that interferometers could be made better by putting in squeeze light, and that was very important to show that. But you could easily just make a better interferometer. You could have made a better interferometer, and in some sense, you made interferometers that weren't as good as you could make, so that you could demonstrate that squeeze light made them better.
Okay, regarding exactly this point, you mentioned that when they try to increase the power, which would be kind of the natural thing to do, right? That they run into instabilities. Is that related with pressure, light pressure, or is it something else, or is it diagnosed, or do they know what they needed to fix?
There's a whole bunch of different things that come in. There's a kind of fundamental thing which turns out not to be the problem, but could be a problem if they manage to increase the power further. So let's discuss that one first, this kind of fundamental thing. And that is that they have these spectacularly good mirrors that have losses of about a part in 10 to the 6th. And those are by putting dielectric coatings on a big piece of, I believe it's sapphire. So you have these coatings on there, and they give you this remarkable reflectivity with very low intrinsic losses. Even so, there's a little bit of intrinsic losses, and the mirrors get heated up. When you got 4 times 10 to the 19 photons per millisecond coming in, even a tiny amount at optical frequencies, even a tiny amount of loss will start to heat up those mirrors. And when they heat up, the coatings start to oscillate. And they oscillate in such a way that they are phase matched both in time, both in frequency and wave number, to scattering light out of the main mode and into another mode. This is a parametric process, and once it sets in, you're screwed. So this is a problem that was pointed out by Brzezinski years ago. I thought it was the problem in turning up the power, but it turns out they pretty well controlled that by managing to damp these parametric instabilities by a bunch of baffles and things in the vacuum tanks. So currently that one's under control. In future interferometers, which will include the Cosmic Explorer in Europe, which I believe is a 10-kilometer interferometer, and will include kind of LIGO, just scaling LIGO up to 40 kilometers. It's called the Cosmic Explorer in LIGO. God, to think about a 40-kilometer interferometer. And it could be down the road here. Anyway, in those, they will almost certainly upgrade the mirrors to be monolithic and not have coatings. And so that problem is likely to go away. The actual problem in turning up the power is, you know, they do have a hard time getting the lasers to produce more power. But I believe the problem is once all this power is running around in the arms, as you said, there's a lot of stuff being pushed around. That is to say, in this idealized picture, you know, there's one mode of mechanical oscillation of the mirrors. They swing back and forth, you know, on a pendulum. But in fact, they are a semi-rigid body, and they're not even that. They have lots of internal mechanical modes, and so they do a lot of mucking around when the light hits them, because this is a lot of power to have them. And of course, they have control mechanisms for that. The whole thing is just a gigantic control device to keep the mirrors not doing anything in those other degrees of freedom. But that got to be very hard to do. The power got this big, and they just found they couldn't do it. But when they tried to push the power up, the things didn't work. So that's a semi-practical problem. Well, all of these are practical problems. They're not fundamental, but it is what kept them from jacking up the power even further.
Okay, thanks. We have a question by Joaquin. You can speak up, Joaquin, if you want.
Thanks. Okay, thanks a lot for the talk. I'm very happy to hear you talking about things I have been trying to read recently. And it's much better to have the author of the paper than reading the paper. Okay, so let me ask you about the second part of your talk at the end, right? When you were showing how you could beat the short noise limit, basically producing entanglement, right, on the photons or whatever quantum state you are using to do your measurement. So now the question, well, I have several questions, but one of them is it realistic to think about entangling the photons in an interferometer like LIGO to the level you would need to beat the short noise limit, or how many photons do you need to entangle to get into the Heisenberg limit, for instance, in LIGO?
In LIGO, you'd need to get to the Heisenberg limit, you'd need to entangle all of them.
Okay, so that's
so,
it. That's
right?
impossible,
That's basically when you put the squeezed light in, it produces the result is entanglement between the arms. It's actually entanglement between the modes in the arms, and those modes would have to be entangled to the level of essentially all the photons being entangled in order to reach the Heisenberg limit. That's why, you know, so the squeezing produces a little bit of entanglement, and then losses after a while meet. Basically, when you say that the losses limit how much you can do with squeezing, The losses are saying, okay, no, after a certain point, you can try to entangle more photons in the arm, but the losses will just remove that entanglement. So here's the limit.
Okay, so with photons, that's not gonna happen, right? I mean, the reaching the Heisenberg limit should be done with some other degree of freedom in a different, of course, experiment, right? To do something else, where you can have a much larger amount of entangled degrees of freedom, right?
So, you know, so atomic interferometers, people actually do use entanglement even now to improve the performance of atomic clocks. So that's perhaps there's another case where entanglement is being used to make better, used in metrology, although I don't think it currently gets past what the best other unentangled clocks can do. But certainly that's been done. And yeah, so the point there is in an atomic clock, you also can make it better just by buying more atoms. And so there will be a trade-off between just buying more atoms and entangling the atoms that you have. I mean, it's very direct. You saw that all of that analysis could be done with about the Kramer amount can be done with atomic interferometers, and it is entanglement, very directly entanglement. It's very directly thinking in terms of entanglement that makes things better. But there will be this trade-off between buying more atoms and buying entanglement, because the entanglement won't be easy. And it's just that for those systems, photons are incredibly cheap. Atoms are a little more expensive. So the trade-off, atoms excited coherently are a little more, are a little easier to get. So the trade-off will occur at a different place. And so people work on that. That's a thing that could be done. And the trade-off will occur at a different place as to when the entanglement, that is the quantum metrology, becomes actually useful compared to just getting more atoms.
Okay, but in any case, I find it really fascinating, this connection between entanglement and quantum metrology. I was only recently get acquainted with this. Okay, thanks a lot. Ernesto, I hand it to you.
Yes, okay. I have a question, maybe it's a bit more technical, and it's not on this wonderful trade-off between experimental concerns and theory. It's more on the theory side. This very last part of the talk that you gave, when you have in the example that you showed to reach the Heisenberg limit, you created the GHZ state, right? A GHZ state. And these states are very sensitive. They're not robust at all, because if you measure a single qubit there, then you spoil the whole thing, right? Are there people working on finding whether other classes of entangled states, which are more robust, might be, yield something close to the Heisenberg bound, but without being so sensitive, because this kind of state engineering might be useful, I guess, right? When you start considering practical methods.
Yeah, this is an absolutely critical question. And, the way you get at that from the squeeze light perspective is, well, the squeeze light, the kind of entanglement it produces is less susceptible to screw up than the, what I call the cat state and what you're calling the GHZ state, less susceptible to screw up by losses. There are certainly people who think about precisely this point about, the cat state is terribly sensitive to losses, and could you do better? And certainly you can do better. You can design states that will achieve that bound in the presence of losses that I wrote down. And, really the expert on that, you should have him give a talk, is Konrad Vanacek. Because they've done a lot of work over many years. I should say Konrad and Rafał Dępowicz-Dobransky. You should have one or both of them give a talk, because that is exactly what they have done, is to ask the question you asked: are there better states that optimize things in the presence of losses? And there are, and you can achieve those kinds of bounds that I wrote down, which a Cascade can't get those at all.
Okay, wonderful. Okay, thanks. I don't think we have more questions now, and we're a bit over time, but it's been a wonderful journey to hear from the theorist idea in 1981 to upgrades that they're doing on the best, most sensitive detector in the world in 2021. It's amazing. It was wonderful to have you here. Thanks again for accepting. And that's it for today. Thanks a lot, Carl, and everybody who attended.
Thank you.
Yeah, thanks. Bye.
See you.
Bye-bye.
Bye-bye.